It's my pleasure to introduce our speaker today, Xinran, who is a PhD candidate in statistics at University of Wisconsin-Madison. Let me get rid of this. So Xinran works in causal inference, topics including generalizability and transposabilities. And in particular, she also works in robust statistic and transfer learning, which we'll be hearing about today. So without any further ado, let's welcome our speaker.
Yeah, thank you for the introduction and thank you for having me. It is my pleasure to introduce to you my work on robust transfer learning with sensitivity analysis. And let me start with a motivating example. So we know that every election runs ad campaigns, but the effectiveness of ad campaigns remains controversial. And a recent work by Agro et al. Has been trying to answer the question about ad campaign for the 2020 US presidential election. In particular, they wanted to answer the question, how would online ads against President Trump affect voter turnout in 5 battleground states, Arizona, Michigan, North Carolina, Pennsylvania, and Wisconsin? And they answered this question by running a randomized experiment on nearly 2 million voters 8 months ahead of the election. So voters were randomized into the treatment or control group. The treatment group received an average of more than 700 ads against Trump through social media, which was roughly 2 ads per day. An example ad is on the right-hand side, which is a story saying that this former Trump voter will not vote for him again because of, quote and unquote, his poor handling of the COVID. And the control group did not receive such ads from this experiment. The outcome of interest was a binary variable indicating whether or not a voter has voted in 2020, so 1 for voted and 0 for not voted. Their effect of interest was the average treatment effect, or ATE, which was the difference in voter turnout between the treatment and control groups, and it turned out to be insignificant. In other words, this large-scale ad campaign cannot change voter turnout on average. And what has actually motivated our work was a quote from their paper, as I quote here. One reasonable question is how well our findings would generalize to other electoral contexts. And we saw that before the 2024 election, and the natural question back then was, would this negative ad against Trump remain ineffective in 2024? Of course, ideally, if you wanted to know about this ad campaign, you would be running another ad campaign in 2024. However, ad campaigns can be very expensive. The particular experiment by Agro et al. Has been costing nearly $9 million. And what we are going to seek is a less than ideal but significantly cheaper approach by using transfer learning. Just give you a sense of that by looking at the simplified data table. So we have the 2020 voters where we observed their demographics like age or gender, and we knew whether they had voted in 2020. We are interested in the 2024 voters in which we had their demographics like age or gender, but we didn't know whether they had voted in 2024. So what transfer learning can do is to transfer the knowledge from 2020 into 2024. But of course, it relies on some assumptions. And a key assumption that is really the motivating question for today is, in this context, can be interpreted as the similar voters in 2024 and 2020 will have the same probability of voting. Unfortunately, this assumption is very unlikely to hold in this context because of the many differences in electoral context between 2020 and 2024. So for example, in 2020, people cared a lot about the COVID, whereas in 2024, there were more concerns on wars, inflation, immigration, and perhaps most surprisingly, Biden has dropped out. So before I introduce the solution to this question, let me give you a broader picture and notation of the data structure that I'm talking about. So in fact, many tasks in data science are instances of such generalization or transfer learning in the sense of involving 2 different populations. There will be a source population P, in which we observe random variables X and O, and there will also be a target population Q, where we observe X. So in the previous election example, the source population P would be the 2020 voters, in which we observe their demographics X, including age and gender, and we also observe some outcome variable of interest, for example, whether a voter has voted. And in the target population Q, where in the context would be the 2024 voters, we only observe some covariates X. Just a bit of more on notation, I'm going to use subscript in P and Q to denote the distribution that are induced by the corresponding random variables. For example, this POX would represent the joint distribution of O and X from the source population, and this QX would be the marginal distribution of X in the target population. And this would be the data that we are working with. The interest here is to learn about some meaningful features of the target distribution. And I'm going to denote that as psi q, where here psi is a functional. I will refer to it as a target function or target estimand. And this QOX, again, is the joint distribution of O and X in the target distribution. Just to give a bit of concrete examples, for example, if I'm interested in the average outcome in the target population, then we can define psi as the expectation of O and the QO, where again, this QO represents the distribution in the target for the random variable O. And more generally, we may define psi as a Z functional in the sense of psi is defined as the solution to this equation, which says the expectation of S should be equal to 0, where here S is a pre-specified function, for example, a score function. And in order to identify and estimate psi, we will need to make assumptions which allow us to use the information from the source samples. And a typical assumption that has been made in the literature is the so-called conditional exchangeability assumption, which says that the conditional distribution of O given X should be identical between the target population Q and the source population P. While this assumption is widely used, it is unfortunately not testable with data because we did not observe O in the target population, and it is also documented to be violated in practice by recent works, which shows the violation of the assumption in many replication studies. So in view of this, the theme of my work would be to conduct robust generalization or transfer learning when key assumptions like conditional exchangeability are implausible. And the specific talk will be divided into two parts. The first part, we will be looking at the analysis of psi, and we try to answer the question, how can we analyze psi if conditional exchangeability is violated? And we'll see how we can use that to answer the motivating question for election. And in the second part, we're going to step back, say before we conduct any analysis, just looking at the design, is there a way to answer the question, which design is less sensitive to the violation of the assumption? So here by design, I'm speaking of it in a very specific context in the two scenarios. The first scenario is that given the data, then which estimand, say mean or median, would change the least when conditional exchangeability is violated. And second is conversely, given an estimand, which data, say source or target data, would lead to the smallest change in the estimand when conditional exchangeability is violated. And I will start with the first part. And before that, do you have any questions on the notation or the background?
Yeah. I'm curious why your core example is one where there was no effect. It seems like if you have no effect, there's two possibilities. Either you have an average effect at 0, or you just have no effect in any individual. While it would seem like you have a positive effect or a negative effect, you would have more to work with because you could think, well, maybe there's heterogeneity, but at least you know there's some effect. So I'm just curious about the choice of example.
You mean why we are looking at the average treatment effect instead of some individual?
So at least, or maybe I'm thinking too much about a particular example, but the case you started with was specifically one where you had no effect in the population, which seems like it might have a little bit of a different structure that if you have, so at least standard treatments of transportability I've seen tend to say you have, some average effect in one population, doesn't generalize to others. The example you started with was one where, if I understood it correctly, there was no effect, or at least.
I see.
Yeah.
So we started with this because the original paper by Agar et al. Started with this average treatment effect on, say, the all population of voters. But we do have some subgroup analysis in our paper to consider some subgroup divided by, say, gender or urbanicity and other characteristics. But for the sake of this talk, I'm going to focus on this because this was the main parameter of interest in the original paper.
So did the subgroup analysis at least suggest that there were subgroup effects?
In the original paper, they also considered subgroup effect, but they were not significant.
Okay, well, thanks.
Yeah. Maybe any other questions?
I think Michael might have one.
No, just a comment saying I like the problem framework. That's good. Thanks.
Okay. Then maybe I can proceed to the first part of the question and recall that our application question was how would online ads against President Trump affect voter turnout for the 2024 voters? And we're going to look at the Pennsylvania voters, or shorted as PA, because that was an important swing state in the election. So our source data P would be coming from the 2020 voters from this aggregate odds experiment, where we observe X, A, and Y. So here X is the voter demographics, including age group, gender, party, and voting history. A is a binary indicator variable of treatment, where A equals to 1 means receiving ads against Trump through the social media. And Y is the binary outcome of voted or not. So I'm going to adopt the potential outcome framework with Suva, saying that Y is one realization of the two potential outcomes, Y parenthesis A, in the sense that if your treatment A equals to 1, then Y equals to Y1, meaning the potential outcome had this voter receive ads against Trump. Whereas when A equals to 0, then the observed Y would equal to Y0, meaning the potential outcome had a voter not been assigned to the treatment. And in the source population, we are going to assume strong ignorability, which says that conditional X, this treatment should be randomized, and also the propensity of getting the treatment should be within 0 and 1. And both parts of this are satisfied by the design of the original aggregate odds experiment, and we're going to assume that throughout this part. Our target population Q would be the 2024 Pennsylvania voters, where we only observe X. So just the data structure, we have the 2020 voters as source population P, where we have X, A, and Y. And Y is one realization of the two potential outcomes. If A equals to 1, Y equals to Y1, and if A equals to 0, then what would equal to Y0. What we are interested in is the 2024 voters, which is the target population, and we observe X. So the actual interest is the difference between Y1 and Y0 on average for the target population, which would represent the ad effect for the 2024 voters. And in notation, this parameter of interest would be the expectation of Y1 minus the expectation of Y0 on the target population Q. And for the simplicity of notation here, in this talk, I'm going to set O equals to Y1 to be consistent with the original notation. And my target functional or target estimate psi here would be a function of QOX defined as the expectation of O under the marginal distribution of QO. So things are similar for the case where O equals to Y0, and I'm just going to focus on Y1 here for the simplicity of notation throughout. And of course, since we don't get to observe O in the target population, we do need to make assumptions, and two assumptions are widely made in this literature, which we call A1 and A2. So A1 is the so-called overlap assumption, saying that the support of QX should be within the support of PX. In other words, we cannot extrapolate beyond the covariance space that we observe from the source data. And the second assumption, A2, which is really the critical assumption here, is called conditional exchangeability. It says that the conditional distribution of O given X should be identical between the source and the target population. And with A1 and A2, we'll be able to identify our target parameter here is the mean of O in the target population. So by first conditional on X in the inner expectation, where here we have this expectation of O given X in the target, which is unobserved from data. And then by A1 and A2, we will be able to replace it with the conditional expectation in the source population, which is then observed or identified from the data we have. And like I said, these two assumptions are widely used, especially in the context of causal inference, and it does allow for the so-called covariance shift in the sense that the marginal distribution between the X, between the source and the target can be different, which in the context means that the voter demographics can shift from 2020 to 2024. But on the other hand, it does not allow for the difference between the two conditional distributions because of A2, meaning that conditional on the voter demographics, the outcome should be identical between the source and target population. And as I said in the beginning, because of the many differences in electoral context between the 2 years, it is very likely that this A2 cannot hold. So our question here is, what if A2 does not hold? And we know in causal inference, the standard answer to this type of question would be through sensitivity analysis. In short, a sensitivity analysis answers the question about how will my analysis of psi change if A2 is violated. And we will proceed in the following 2 steps. The first step, we will be specifying a sensitivity model in which we introduce a sensitivity parameter gamma in order to quantify the violation of A2. When gamma equals to 0, this means A2 holds, and when gamma not equal to 0, this means A2 is violated. And wanted to stress that here we will be introducing this gamma in order to answer this type of question for sensitivity analysis, but gamma is not a parameter that can be estimated from the observed data. And after that, we will be using the sensitivity model to make analysis on estimating psi. And let me start with the first part of modeling. We are going to use the notation of Q gamma in the superscript gamma to denote the target conditional distribution indexed by the sensitivity parameter gamma. And we're going to assume that instead of thinking about the case of conditional exchangeability, we're going to assume a violation of the assumption in this particular form. So here, F represents the density function. So the numerator would be the conditional density of O given X under the target distribution Q. And the denominator would be the conditional density of O given X for the source population P. So we are going to assume that the density ratio between the 2 conditional distributions is proportional to exponential gamma O, where gamma is the proposed sensitivity parameter. If gamma equals to 0, then the right-hand side would be 1, meaning that the numerator and denominator equalize, which will return back to the case where A2 holds, or in other words, in this case, the conditional exchangeability assumption would be holding. Or notation-wise, this means Q0 equals to P. And when gamma is not 0, then A2 will be violated in a degree that is quantified by gamma. Just to be more concrete, in the case where O is binary, for example, in our case where O equals to 1 for voted and 0 for not voted, then gamma would be measuring the violation in terms of odds ratio, in the sense that the odds ratio between the target and the source sample would be exponential gamma. For example, if exponential gamma is 1.05, then that would mean for a voter who received ads against Trump, the odds of voting in 2024 would be 1.05 times the odds of voting in 2020. And before I move on, do you have any questions? All right, so now that we have the model, before we understand how we use this model, let me take a moment to express why we use this model. So first, this model is widely used in missing data, causal inference, and context of transportability and generalizability, which is closest to our context. There are many reasons people go for it. The important reason that we use it is first, it makes inference on psi tractable in terms of asymptotic normality. And it also leads to new insights on robust designs, which I will be talking about in the second part of it. Well, all models have pros and cons. We wanted to stress that in some sense, since sensitivity models concern unobserved data, most sensitivity models are wrong, but you will see from both parts of this talk that this particular one is useful, as also documented in the literature. So with the small sensitivity model as well as the overlap assumption A1, we will be able to identify the target parameter. So we first introduce this notation Q gamma on the joint distribution to be the target distribution induced from the sensitivity model. And heuristically, for our target estimand psi, which now becomes a function of Q gamma, we can identify it by first conditional X, and then jointly with the marginal distribution of Qx in the target population. And in the specific example where we are interested in the expectation of O in a target population, and O is a binary variable of 1 or 0, then the psi functional can be identified as follows. So here is the identification formula for the expectation of O in the target population, where here the outer expectation is taken over Qx, which is the covariate distribution in the target population. And inside this expectation is an exponentially tutored version of mu x, where here mu x is defined as an outcome regression function. It's the expectation of y given x on the treatment group. Or in other words, this is the conditional voter turnout for the treatment group in the source population. And after we have identified our target functional, then for any given gamma, we would be able to estimate this psi. And we're going to propose two different ways of estimators, and we'll discuss them briefly. So the first estimator would be the simple plugin estimator directly motivated by this form. In the first step, we will estimate mu x from the source data. And then after having an estimate, say mu hat, we will average the exponentially tilted version of mu hat among the target sample. So here, suppose we have IID samples from the target sample indexed by I belongs to IQ, then this would be the plugin estimator that we propose, where here this average is taken over the samples on the target sample, and then inside this summation, it would be the exponentially tilted version of this mu hat, which is again the outcome regression function. After having this, we propose to construct confidence intervals, or shortened as CI, with a two-sample nonparametric bootstrap. And our paper shows that under regularity conditions, this estimator is consistent, asymptotically normal, and this particular bootstrap procedure will give us an asymptotically valid confidence interval. And now that this plugin estimator has these nice properties and is very simple to implement, there's also a very popular estimator in the literature of causal inference, especially recent years, based on the so-called efficient influence functions, or EIFs. There are many reasons that people may go for EIF-based estimators, and one important reason is that the EIF-based estimator has doubly robust rates. So if you're not familiar with doubly robust rate, I'm going to give an example under this context on the explanation of doubly robust. So suppose when A2 holds, meaning that the conditional exchangeability assumption holds or gamma equals to 0, then it turned out that the EF-based estimator would involve three nuisance functions. So here mu x is the outcome regression function we have seen, and pi x and omega x, well, I'm not going into detail here. These are two different weighting functions, where pi x weights between the treating and control groups, and the omega x weights the covariance between the source and target sample. So in order for the EF-based estimator to have asymptotic normality, we will need some conditions on the estimation rates for these nuisance functions. And in this case, the condition we need would be the two formulas, dr1 and dr2, where dr stands for doubly robust. At a first glance, if we look at these formulas, you will find that instead of assuming or requiring any of the nuisance function to be estimated as a certain rate, we only need the product of the estimation rate of two nuisance functions. So for example, in the first equation, if we estimate pi x in a sufficiently fast rate, then that could compensate for the potential slower rate for the other nuisance function mu hat. And that is the name doubly robust coming from. And we wanted to see in our context where gamma is not 0, what the efficient influence function based estimator looks like and whether we might have this doubly robust property. And it turned out that in the case where our sensitivity model holds, given gamma, this would be the estimator based on the efficient influence function. And it consists of two parts. The first part is the plugin estimator we have seen before. And the second part, well, I'm not going into details. Briefly, it will be an average over the source samples, where here NP is the sample size for the source, and this I belongs to IP is the samples from the source population. And then this would be some complicated weighting and exponential tilting form times this y minus mu hat, which is the residual term. And it turns out that under the standard regularity conditions, this EF-based estimator will be asymptotically normal and semi-parametric efficient if dr1, dr2, and this third condition holds. So dr1 and dr2 are the two doubly robust conditions, but you may notice that the third condition is solely on the estimation of mu hat, meaning that estimating the other two nuisance functions sufficiently fast will not compensate for the potential slower rate for this outcome regression function. Or in other words, the estimator does not have doubly robust rates. And so because of this, in practice, we would recommend you start with the estimator based on the simple plugin estimation, and we may proceed to the EF-based estimator for a broader context. And do you have any questions for this? Okay, if no questions, then let's see what we can do with the either of the estimators. Recall that our interest population is the 2020 voters in Pennsylvania, and let's give you an example of the ad effect in Philadelphia, which is the most populous county in Pennsylvania. So first, before we do any sensitivity analysis, suppose A2 holds and gamma equals to 0, meaning that there's no unmeasured differences between the 2 years. Then it turned out that the ad effect is insignificant. And then after we consider this violation of the assumption with a small range of gamma, which in odds ratio scale, this would be between 0.95 and 1.05, then this would be the result. So suppose we start with some gamma, which is negative 0.05, and we have estimated the ad effect with the plugin estimator, and we found the p-value, which turned out to be significant and negative. And then we proceed on this list by changing gamma for some different value, and turn out this case, the ad effect is insignificant. And we may go on in this table, and it turned out that for some other values of gamma, this ad effect would be significant and positive. So if you look at this table, a natural question might be, which role should I look at, since they seem to correspond to completely different conclusions? Or in other words, which is a plausible sensitivity parameter that I should interpret my results? And in fact, in sensitivity analysis, there's a long-standing question of what is a large, small, or plausible value of the sensitivity parameter, which is gamma in our context. Of course, if you are a domain expert, you maybe specify a range, say C, and estimate this ad effect with gamma within the specified range C. But for people who may not have the domain expertise, we will need to use some benchmarking or calibrating approaches in order to find a plausible range for the sensitivity parameter. The most popular approach here would be to omit one variable from X, and it is quite popular, it has pros and cons, that has been documented in the literature. And today I'm going to propose a different approach based on the dissimilar partition of the source data. The key idea would be to find gamma that reflects differences between the two 2020 subsets and use that as a proxy for the difference between 2020 and 2024. So recall that we have the source randomized control trial, or RCT, and we are going to partition it into two dissimilar subsets, S1 and S2. And I'm using different colors to indicate that these two subsets should be dissimilar. And in our context, we use Rust Belt states and Sun Belt states. And I'm going to treat this S2 as the proxy target and try to estimate the ATE in this S2 subset using two approaches. Either we could use it by the RCT data on itself, and I will denote the corresponding confidence interval as the oracle CI, since it represents the true ATE on the subset S2. And alternatively, the other approach we're going to take is to transport from the S1 subset with a branch of gamma, and we call this transported CI because it was transported from S1. And we're going to define a plausible range C as the gamma such that the transported CI overlaps with the oracle CI. Or in other words, these gamma would be the measuring the difference between S1 and S2, and we're going to use that as a proxy for difference between 2020 and 2024. Of course, as you may have already observed, C does not reflect the true unmeasured differences between 2020 and 2024, but it would be a useful way to rule out gamma that are too realistic to be true, and you will see that in the later slides. But before we move on, do you have any questions? Cool. So let's see what we can get from the actual data. We had the Philadelphia County, and we had a bunch of results that has different conclusions. And we're using this calibrating approach, and it turned out that we did rule out some possibilities. Notably, we have ruled out the case where the add effect were negative, meaning that even if there may exist plausible differences between 2020 and 2024, running this ad campaign against Trump will not lower the voter turnout in Philadelphia, which makes sense because Philadelphia is the most demographically leaning county in Pennsylvania. And of course, in some cases, the ad effect could be significant and positive in Philadelphia, and there's some plausible change between the 2 years of election, which means that the ad effect can increase the Philadelphia's voter turnout in 2024. With the same idea, we are going to apply it for every county in Pennsylvania. And so first, before any sensitivity analysis, when A2 holds with gamma equals to 0, then it turns out that the ad effect will be insignificant in most counties except for one county, which is Fulton. So if you're not familiar with Pennsylvania, Fulton is actually the most Republican-leaning county in Pennsylvania. So this result is saying that if there are no unmeasured differences between 2020 and 2024, then running an ad campaign against President Trump would lower the turnout in Fulton significantly. And suppose there are violations of the assumption, or in other words, gamma is not equal to 0, then using our calibration approach, this would be the result. So here is Philadelphia, which is blue, meaning that there could be some gamma that leads to significant and positive effect in Philadelphia. And it turned out that Philadelphia is the only county in Pennsylvania that could have a positive effect. In fact, for the majority counties in Pennsylvania, which are colored in red, the ad effect could only be negative, meaning that the ad against Trump could only lower the turnout in most of the counties in Pennsylvania. And you can see there are also some places in gray, meaning that even if there exists some unmeasured differences between the 2 years of election, the ad campaign will also still have no effect on average. And this would include Allegheny, which is a county that Pittsburgh is located. So in summary, in this part of the talk, we have discussed how do we analyze psi in the application of the voter turnout, in which we proposed a sensitivity model based on exponential tilting, and we show the identification and estimation of psi, followed by a calibration procedure that helps us find the plausible range of the sensitivity parameters so that we can conduct a meaningful transfer learning between the ad campaigns in the 2 years of election. So now let's move on to the next part, which is stepping back from analysis. What is the design of robust studies? And before we move on, let me take a moment to visually think of what we have done in the previous part. So here I'm plotting gamma in the x-axis, where the midpoint is gamma equals to 0, where represents assumption A2, which is conditional exchangeability. And I'm plotting our target function, or estimand psi, which is a function of Q gamma on the y-axis. And so here, this red curve would represent the psi as a function of gamma. So what we have seen before is that suppose we have a gamma which is in a small range around 0, then how would that result in different values of psi? And we try to interpret that estimate of psi. And a natural question here is that suppose I have a different psi functional, say psi tilde as a different target functional, and it may have similar values with psi when the conditional exchangeability assumption holds. However, the psi tilde function changes with gamma in a different way, so that if we perturb gamma again in a small range around 0, you may find, in this case, a shorter change in psi tilde for this new functional. So comparing the two plots, you will find that perhaps the psi tilde would be less sensitive than psi when the assumption is violated by a small range. Or in other words, we are curious about the question, which estimand, say mean or median, would be less sensitive when A2 is violated. And similarly, if we have two different target populations, say Q or Q tilde, then with the same target functional psi, then a natural question is which data set, say Maryland or Wisconsin, would be less sensitive when A2 is violated. And in order to answer the question of sensitivity, we will notice that a natural answer from math or calculus answering the sensitivity of the change in the y-axis when the x-axis is perturbed around some value would be through derivatives. And that's the proposal that we're going for the second part of the talk, in which we'll be proposing some measure called slope that is a derivative-based measure of sensitivity motivated by this visual illustration. So recall that we had the sensitivity model, which is based on the density ratio that is proportional to exponential gamma O. And we're going to propose this measure, which is called the sensitivity to local perturbation from exchangeability or slope as the derivative of psi with respect to gamma when gamma equals to 0. Or visually in this plot, the slope is literally the slope of the tangent line of this psi curve around gamma equals to 0. So as the motivation also the definition suggests, the slope would be a measure of the sensitivity of the particular design in the sense that a higher slope would indicate that this estimand would change more drastically under local violations of the assumption A2, and therefore the underlying question would be more sensitive to violation of the conditional exchangeability. And this idea actually is also similar to the ideas in robust statistics, from which Huber has mentioned in his book that robustness signifies insensitivity to small deviations from the assumptions. And also, as you might have seen from the notation, the slope depends on two arguments. So here, this Q0 is the target distribution had conditional exchangeability assumption holds, and the psi is our target estimand. So as we mentioned in the beginning, slope can then be used to compare two different functionals, say psi and psi tilde, or comparing two different distributions, say Q or Q tilde, in terms of their sensitivity with respect to the violation of the assumption. And here I wanted to stress that slope is really a measure of the sensitivity at the population level, which means that this represents our conceptual idea that one design can be intrinsically more or less sensitive than the other design, irrespective of what estimation procedure is in use. So for example, the value of slope is agnostic to how psi is estimated. See, whether you are using the plugin estimator or the efficient influence function-based estimator should not change the slope as a measure of the underlying design. And this is in contrast to most works in sensitivity analysis. So if you're familiar with the literature of robust statistics, you may find that slope is actually analogous to the very well-known robust measures, which is the influence function proposed by Hampel as a local derivative. So the similarity is that influence function was also defined as a local derivative with respect to gamma equals to 0. But the difference is that the perturbation model from Hampel is slightly different. So in our case, we defined the perturbation based on this exponential tilting, whereas in Hampel, he defined this perturbation based on the point contamination, in which the original distribution Q0 was contaminated by a point mass at some new point. And the contamination proportion is characterized by gamma, where here the delta is the direct measure at a new point. And in fact, slope is not only analogous to influence function conceptually, it does has an analytical relationship between slope and influence function. So under sufficient regularity conditions, we have shown that slope indeed has this form, where here this expectation is taken over the target distribution had the conditional exchangeability assumption holds, and inside the expectation is the product of two terms. The first term is the influence function, and the second term is the residual, which is O minus mu x, where we recall that mu x is the expectation of O given x in the source population. Or in other words, the slope is the projection of the influence function onto the residual space. And this not only gives us a geometric interpretation, but also gives us a formula for slope. So as long as you know the influence function, you will be able to find the formula for slope. And with that, let's see what we can get from the real data. And I will go back to the toy example that on the voting data, where our target functional psi is the mean functional, which is the expectation of O in the target population. And suppose O is a binary variable where O equals to 1 means vote, right? So here we are solely considering the voter turnout without any ad campaign or causal element of it. And it's just for illustration as a toy example. So the question here is that which county in Pennsylvania, which serves as the source county, would be least sensitive when generalizing to the rest of Pennsylvania, which will serve as the target county. And in this case, it turns out that the slope for the mean functional would have this form, where this is an expectation taken over Qx, the marginal distribution of x in the target population. And inside the expectation is the sigma squared x function, which is defined as the conditional variance of O given x in the source population. Or in other words, the slope for the mean functional is characterizing the heterodicity of the outcome in the source population, evaluated over the covariance space of the target. And I wanted to note that this formula holds in general, not only for a binary outcome, but also generally for any outcome variable that has a second moment. This would be the case for the slope. And we can use that to estimate the slope for each county as the source and the rest as the target. And this would be the result of slope on the map of Pennsylvania, whereas the out county would have the smallest slope and the Philadelphia county would have the highest slope. So while I'm not an expert in political science, it still makes a lot of sense to me that the Philadelphia has the largest slope, since as you can see from the previous example, Philadelphia is probably not the most representative county in Pennsylvania. So to summarize, in the part 2, we have talked about the design of robust studies, in which we propose a measure called slope, which is a simple derivative-based metric that measures the robustness of study design, and it is shown to be connected to Hampel's influence function. With slope, we will be able to compare robustness between the study designs. And do you have any questions about the 2 parts before I move on to the future directions?
Yeah, so I wanted to ask about sort of that positive proposal of using within population variation in gamma in order to do the extrapolation. And the first part of the question is just, so it seems like how that works is going to be sensitive to how you partition the population. So you do it in terms of counties. If you did it in any other way, you would get presumably a different pattern. And you could also do it in terms of more traditional subpopulations. So you could partition a population in terms of gender or or more specific descriptions of the counties in terms of political. So the first thought is just that the way you do the partition seems to matter a lot. And the question there is sort of how do you think of that? And then the second part of the question is that so the way you're doing this seems a little bit indirect in the sense that sort of gamma is clearly a proxy for other effect modifiers. So what's the advantage of this approach as opposed to actually trying to more directly measure effect modifiers and then do something like reweighting? Something that's the way that someone like Barenboim would do it, his approach. So there's a bunch there.
Yeah, I see. Let me reinterpret the question in case I'm correct me if that's not your question. The first question is about choosing the subpopulation. So in my case, I'm using in the previous example, we are estimating the ad effect for the entire population, and it could be a legitimate question on which subpopulation you might be looking at. And that's a good part. I would say that, again, the reason we chose the particular one was because of the original analysis. But indeed, choosing different subsets will lead to different extrapolation results on the target sample. And I would say that if you think of the slope measure as a way to measure the sensitivity of different populations, using slope would help us to find which population is the least sensitive to which subpopulation is the least sensitive to generalize from, and which subpopulation would be the most sensitive to generalize from. So that would be one way of thinking about the difference across different subpopulations. And of course, there is also the scientific perspective of what is more interesting to political scientists. And that would be also a different aspect of choosing the right subpopulation to generalize from. And the second question is of gamma. So I think my understanding of the question is that, yes, you could measure, you could propose this sensitivity analysis, but why not just collect more data, right? You can collect more X, and then that would help the assumption A2 to hold, and then we don't have any of the questions of say violation of the assumption. So I think on the high level that I would agree that trying to satisfy the overlap assumption and also collecting as much X as possible in order to satisfy A2 is perhaps the most right way of tackling this kind of challenges. But in real data, in many cases, it's very hard to collect all the modifiers of interest. So for example, in the election data, for the voters registration database, there are specified covariates that we can access publicly, and for many other variables, there might be privacy concerns or other concerns that it cannot be released to us. So what we get is a very small subset of the covariates that can be used. So in that case, it would be very important to use sensitivity analysis to see how the conclusions would change when there exists, when we don't get to observe all the effect modifiers. So are there other questions, or maybe I can proceed to the last part of my talk? So the last part would be the future directions, and I will be talking about two parts. The first is about the modeling, and the second is about data modalities. And in this talk, we have been focusing on the specific sensitivity model based on the exponential tuning of density ratios. And as I mentioned, especially in this context, most, if not all, models are wrong, and we really wanted models that are useful. And the particular ones that I'm interested would be to account for the difference between P and Q in a more flexible way. So first is that the conditional change of O given X could be modeled differently by allowing for, say, bound-based sensitivity models, which are more popular in the literature, and also some minimax robust models, which again goes back to Huber and also has some recent development. And another idea that I'm really interested in is based on the perturbation in X, which could in part answers the question of what if the overlap is violated, which is also a very important question in the literature, not only in generalizability, but also in general in causal inference. And with any of the models, the goals that I'm interested in is really want to be useful in design and analysis, in the sense of which data is more robust, which estimand or functional would be more resilient, and how do we make robust decisions and conclusions. And since the majority of the literature here would be focusing on the analysis or inference part, and what I'm really interested in is as I mentioned in the slope project, is I'm interested in thinking more about what data and what the actual statistical functional would be more robust when there may exist violations to the assumptions. And following that, I'm also interested in generalizing the form of data modalities in the sense to answer the question, how do we collect, evaluate, and use data in a more flexible and robust ways? And in this talk, we will be focusing on this specific data structure where we have two populations, P and Q. So in Q, we observe X and we don't observe O. And in P, we observe both X and O. In practice, you may be encountering some unstructured data like text or image, and you may get some predictions based on some ML or some fancy AI methods. So an important question is, how do we incorporate these AI predictions efficiently and faithfully? So efficient in the sense of power and faithful in the sense of not introducing extra bias. Of course, you may also be able to get some P tilde that is synthetic or generated from P, and then the question would be, how do we evaluate synthetic data before actually using them in practice? And beyond that, I'm also interested in the case if, for example, like the question has mentioned, suppose we know all the effect modifiers and from X1 to X2, X1 to X5, but the question is really we don't get to observe all of them. Then the natural question is, under some budget or some privacy concerns, we may want to collect some information in the target population. And we really wanted to know how do we more informatively collect data to reduce bias or MSE that could be incurred from the missing other variables. And with that, I wanted to give a final summary of this talk. So my research is really about robust generalization for multi-source and heterogeneous data. And beyond this talk, I've also had some other works in mediation analysis, prediction-powered inference, and also survival analysis, which can be found from my website. And I would really wanted to thank you for your attention and questions, and many thanks for all these people who have helped me, especially my advisor, Hans Kang. And I'm going to leave it on this page with the 2 papers, and I'm also happy to take further questions.
Thank you, Shinran. That was a great talk.
Thank you.
I'll ask a quick question, or maybe it's not quick. So do you have a sense of what kinds of unmeasured confounding or effect modification would be the effect of what kind of unmeasured variables would be underestimated by the exponential tilt model? Like you said at the beginning, no sensitivity model is right, but this one is useful. And I'm wondering if you have thought about or can characterize or could explain to a political scientist what might go wrong under this assumed model.
So I think one thing is, as I would say, restriction of the model is that it is requiring that the odds ratio change is identical across all x. So for example, this is a function of O only. This does not depend on x. So this model might go wrong if there's a high variability in the effect with respect to different x. And that would be one reason that this might go wrong. And important x variable in this context might be race and party. I would say that would be very important. And also gender, urbanicity. Those are the variables that can make this model wrong. But in our data, this variability is relatively small. So that's also one of the reasons we think it's fine to keep this model. But of course, you may enhance this model by making the right-hand side more complicated, but that would be at the cost of difficulty in interpreting the parameters.
Great.
Any more questions in the room? Okay, I guess let's thank again for our speakers for this wonderful talk.
Yeah, thank you for listening.
Yeah.